Okay, so this is the last video for Unit 5. Okay, so again, remember Unit 5 is we're focusing around linear momentum, right? And so in physics, and so this is a video on collisions, sorry. So what happens before we were talking about explosions towards the end of that, the prior video on conservation of momentum. So in physics, a collision is a situation where two objects free from external forces strike at one another. And so just some two common examples, or some three common examples, you'll have like two pool balls, right, or billiard balls colliding on a table, right? So like the cue ball colliding with like the 8 ball, right? That's just one type of collision. Another one, you know, an accident between two cars. And then, of course, my personal favorite, right, a body check in hockey between two hockey players. So these are all just, you have two objects coming at each other, or in some scenario, that are colliding, right? So they're going to essentially exert forces on each other. But remember, they're free from anything from the outside. So when we talk about these, we always make the assumption that there's no friction involved and so forth. And so remember that momentum can be conserved even though most or even all of a system's kinetic energy is converted to other forms of energy such as heat, right, and sound. So these are the two big ones that when we talk, if there's any kind of loss of momentum or so forth, it's generally heat and sound. Okay, but the fact that kinetic energy can be conserved or not conserved is what sets collisions apart. So there's all kinds of different types of collisions, but really there's not all kinds. There's two, but you'll see we have we'll talk about three types. So collisions are categorized according to what happens to the kinetic energy of the system of motion. So of the system, right? And so this is very important to note, is that regardless of what's happening, the momentum is always conserved. Okay. Now, a collision in which the kinetic energy is conserved or unchanged is referred to as an elastic collision. And so during these collisions, the objects will rebound. Oftentimes it's what really is why we call them elastic, because they like bounce off each other. So they rebound elastically after the collision with no loss of energy to heat or deformation. Again, remember, we're talking isolated systems. And so remember that no mass is going to get lost through the process. Now, when kinetic energy is not conserved, the collision is said to be an inelastic collision. In these collisions, part of the initial kinetic energy is actually converted to sound, heat, or deformation. And then there's another type of inelastic collision. So an inelastic collision where the objects will hit and stick together is what we call perfectly inelastic. Alright, so it'd be like two train cars hitting and coupling together and they go off. Basically what happens is after the collision, it's one big mass, right, traveling at a speed. So in these types of collisions, they'll convert the maximum amount of kinetic energy to other forms of energies. And so the basic problem solving strategy here is we're going to use that conservation of momentum, right? So the idea that P before, right, that P total before equals P total after, right? And so again, it's going to look weird because you're going to have all this stuff like M times V. You can have like as many M times V's for each, as many objects you have. But just like when we did energy, things will cancel out, right? Things simplify. Things will be, if it's at rest, then your momentum is zero. Okay, so things happen to make a very long, complicated looking equation to make it look simple. All right, so here's one that's completely or perfectly inelastic, which means they're going to stick together. Okay, so on a touchdown attempt, a 95 kilogram running back runs toward the end zone at 3.75 meters per second. An 11 kilogram linebacker or 111 kilogram linebacker moving at 4.10 meters per second meets the runner in a head-on collision. If the two players stick together, does the running back score the touchdown? So basically, to determine that is our V final positive or negative? If it's positive, they score. If it's negative, they don't score. Okay, and so that's where we're going to use our P before, P after. Okay, and so we're going to say P before equals P after. Okay, and so we would have mass 1, velocity 1, right, plus mass 2 times velocity 2. That's our total momentum. And then we would have the sum of the masses, because remember, they're going to hit and stick together, and that's going to equal our final velocity. And so it'll be m1 v1 plus m2 v2 over our total mass. Okay. Now, one thing you have to note that that the velocities are going to be in opposite directions, right? So one has to be negative. So 3.75 plus 111 times negative 4.10. And then you're going to do 111 plus 95. And you're going to find that you get a velocity of negative 0.480 meters per second, which means the running back does not score. Right, so doesn't score the touchdown, right? Because our velocity ended up being negative. So sometimes you're going to run into problems, especially with elastic collisions, where you do have to apply the conservation of energy, but understanding that you may also have to apply, conservation of momentum. So you have to apply really both of the main conservation laws that we've talked about. Now, so what happens is, and this is going to be something you're going to have to memorize, though, is that through conservation of momentum, conservation of kinetic energy, and some algebra, you can get a formula that relates all the velocities together. Okay, and then so it's just simply the velocities of the second object, or whichever way you want to write this, because this is going to be addition. So basically, the sum of the velocities have to equal each other. Okay, and it doesn't matter if the masses are different, or if they're if they're drastically different. It's like a bullet and a block or something like that. And you can see I do have a little thing here. I'll post a video to show you this derivation, because it's going to take a lot longer than what I really need to show you here. But that's going to be helpful in this first example with an elastic collision. So this is in a billiards game. One player hits the cue ball towards another ball. The cue ball has a mass of 0.1 kilograms. It hits the other ball at the velocity of 2 meters per second. If the collision is completely elastic, the cue ball travels with the velocity of 0.8 meters per second after the collision. And then what is the mass of the and velocity of the other ball? Okay, so I'm going to split this into two sections, right? So on this side, I'm going to use momentum, but I'm going to find the mass of the ball using momentum. And then on this side, I'm going to use kinetic energy, where I'll find the speed or velocity of the ball. Okay, so when I write, right, P before equals P after, or P initial equals P final, right, conservation momentum, then I expand it out to say M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. Right, so I got four terms there, but remember, the second ball is at rest. Okay, so that's important for us to know. Now, we don't know this quantity right here, but we can use that kind of relationship of the sum of the masses. So V1 initial plus V2, or V1 final equals V2 initial plus V2 final. But remember, V2 initial is 0, so that goes away. So it just tells us that V2 final is the sum of V1 and the two velocities of the first ball. And so I can just kind of keep doing some algebra. So M1 V1 initial equals M1 V1 final plus M2 times that sum. So V1 initial plus V1 final. right? Expand this out. This becomes M2 V1 initial plus M2 V1 final, right? Plus M1 V1 final equals M1 V1 initial, right? So get everything over there that is not M2. Actually, you know what? We don't need to expand it because it would be easier for us to not expand, right? Because I'm gonna subtract over that M1 V1 initial minus M1 V1 final equals M2 times V1 initial plus V1 final. And so that just becomes M2 equals M1 V1 initial minus M1 V1 final over V1 initial plus V1 final, right? And so it's going to be, and you could do a little bit of algebra here, just saying that this would be M1 times V1 initial minus V1 final, and so it just kind of cleans it up a little bit. So it's going to be 0.1 times 2 minus 0.8 over 2 plus 0.8. Okay, and you're going to find that the velocity or the mass is going to be 0.043 kilograms. Okay, so that's going to be mass of M2. Now we're going to go to the energy side and now find the velocity. So M1 V1 initial squared, or 1/2, sorry, plus 1/2 M2 V2 initial squared equals 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. So again, this is going to be 0, right? And this is what we're looking for, so we don't have to do anything with that relationship. I can cancel out a halves, and so I get M1 V1 initial squared equals M1 V1 final squared plus M2 V2 final squared. Do a little bit of algebra, so we're going to get M1 times V1 initial squared minus V1 final squared equals M2 V2 final squared. Divide everything by M2, right, and take the square roots. I'm going to V2 final is going to be M1 times V1 initial squared minus V1 final squared, all that over M2. Alright, and so I'm going to get V2 final equals the square root of 0.1 times 2 squared. So 2 squared minus 0.8 squared over 0.043, which is what we found in our previous one. And you find that it's going to be 2.8 meters per second. Okay, and so, but if you kind of go back, if I scroll up here real quick, and I look at this formula, the V2, right? Well, our V2 initial, oops, sorry, chose the wrong. So our V2 initial was 0. So it's basically saying that V2 final equals V1 initial plus V1 final. Well, it's 2, right? 0.0 plus 0.8, right? I would only recommend using this, kind of in a pinch, but you could see that we got the same answer, right? If I used the process of energy, right, or if you can, because the AP they don't give you this, so you'd have to memorize it. And so, like, if you do that, if you want to use that equation, you need to make sure that that you can, or if you use that equation, then you can just use momentum to find the mass very easily, because now you know what V2F, and you don't have to make this substitution right here. Okay, so the last example is a ballistic pendulum, right? And so this is something that they will time to time put on the exam. Okay, so basically a ballistic pendulum, I'm going to shoot something, right? I'm going to project like a bullet or something at a block or something else. Okay, and it's going to move off together, right? So it's going to be a combined mass after. So these can get tricky in the sense that you may have to also focus on a little bit of conservation of energy. In particular, if I want to find out how fast this is moving before or as it moves up, okay, I would need to use conservation of energy. And so there's another equation, right? Because if you read through this, it gives you an angle, right, of deflection basically. So if you use, and I know in previous videos I've used capital L. So to find how high did it move, right? Because it'll move up a height, right? To find how high it moves, you would use the L minus L cosine theta. And so if I just look at the bullet block system, right, just this right here, okay, it's going to be E before equals E after. Then we do 1/2 mv squared, v initial squared, plus mgh initial equals 1/2 mv final squared plus mgh final. Okay, and so again, when we did conservation of energy, things cancel out. So like this is the mghi is going to cancel out because we're going to call the lowest point 0. This is the 1/2 mv's final square is going to cancel out because it has to stop at this point. So our final velocity would be 0. So I end up with 1/2 mv initial squared equals mgh final, right? M's cancel out, and I'm going to solve this for v initial squared, and it ends up being that kind of 2hg final that we've gotten in the past, right? But this h final, we're going to do h equals 1.25 minus 1.25 cosine 6. Okay, you can plug it in there, or you can do that in a calculator. It's going to be a small number because cosine of 6 is a small number. So this is going to be the height's going to move as 0.000685 meters, right? And then I can just plug that in. V equals 2 times 10 times that number, 0.00685. Take the square root of that. And I find that it's moving off at 0.37 meters per second, right? So that would be the velocity before it swings up, which is actually the final velocity, right, of our in our momentum portion. Okay, so now I can trace this back to find the speed of the bullet, because that's what it's looking for, right? What is the initial speed of the bullet? And so I can use P before equals P after, and so it's going to be M1 V1 initial plus M2 V2 initial equals M1 plus M2 times V final. And so this is what I'm solving for, the initial velocity of the bullet. The block's not moving to start, so it's going to be 0. So the initial velocity of the bullet is just going to be M1 plus M2 V final over M1. And so that'll be 4 kilograms, because the mass of the block. You have to convert the mass of the bullet to kilograms, so divide 2 by 1,000. Our final velocity is 0.37, right? Or because that's the velocity of the swinging block, and then divided by the mass of the bullet, because we're looking for what is the velocity of the bullet. So you do 4 plus 0.002 times 0.37 divided by 0.002, and you get that the bullet was fired at the block at a speed of 740 meters per second. Okay, so that wraps up Unit 5 of momentum. After this unit, we'll move into Unit 6. And so have fun with this momentum unit. It's a great unit.